So we'll continue discussing our curvature, and we're going to look at a specific example. We're going to look at this function here. Oh, that should be I, sorry. I'm going to do I, not J. Plus A sine T J. Mind you, this is a circle of radius A centered at 0, 0. You can show that pretty quickly. We know that a circle of radius A centered at 0, 0 in rectangular form would have this equation: x squared plus y squared equals a squared. Okay? So if we take this parameterized version here, this vector function, and we sub in the components, a cosine t squared plus a sine t squared, let's see what we get. What I'm trying to find out is, will this vector function point to points that are on this circle that we know the equation of so well? That we know for sure. Well, you square this, you're going to get a squared cosine squared t plus a squared sine squared t. But that's really a squared times cosine squared t plus sine squared t. All right? But that's just a squared. And that's exactly what we're hoping for, right? What we've just shown is that this was x, right? And there's y. So we just showed that x squared plus y squared equals a squared. So this vector function creates a set of vectors that points to points that are on the circle of radius A. So that's how we know. All right, so I'm interested in looking at the curvature of the circle. So here's our formula for our circle. Let's do a little bit of talking. Ready? So here we go. This is how we define curvature. We said K was equal to dt ds, where capital T is the unit tangent vector, and ds is small change in the amount of arc we've traversed, or arc length. All right, this is true. This is just some facts that would be true. There we go. Now, it's time for a special realization. Okay? You can see these dt's would cancel, and you'd get back this original expression. So this is okay to do, but here's where I'd like you to have a realization that would be nice to know. All right. This thing, ds dt, if you think about that, that's really asking us to take the derivative of the arc length function. Okay? So let's just write down the arc length function for a moment, and we'll be able to see something pretty nice. Okay. Well, the arc length function, we said, we wrote it as s of t equals the integral from 0 to t, the norm of r prime of u, du. Well, so the question is, if that's true, what would ds dt have to equal? So the answer to this is equal to the norm of r prime of t dt. That's actually because of, or by, fundamental theorem of calculus. That's one of the parts of fundamental theorem of calculus. You're taking the derivative of the antiderivative, and of getting back the thing you're integrating, with that expression basically getting plugged in. Okay, there's reasons for that, but that's what's true. So I'm saying that because now we can rewrite this thing here. Instead of writing the norm of ds dt, we can write the norm of r prime of t, like that. Okay. And so what I'm doing is I'm coming up with a new way to write curvature. Now this thing on the top, we write d capital T dt. We can write that in shorthand also, and we end up with curvature is equal to the norm of t prime of little t, okay, and then on the bottom, the norm of r prime of t. Or we can just write it this way. Okay? Now, this is sort of a nice way to write curvature because it's written in terms of things that we know. For example, we would know r of t. We couldn't even ask for curvature unless we had a function. So we would be able to find r prime of t pretty easily. And we know how to find t prime of t also, because you can find the unit tangent vector. And then once we found the unit tangent vector, we can take the derivative of that. So that's sort of nice. And it's a little easier to deal with than the original definition of curvature. While we intuitively understand what this is, we've talked a lot about why this ds is on the bottom, right? It would be annoying every time we had a vector function to go and reparameterize it in terms of arc length, which I'm trying to avoid. I'd rather not have to do that. And that's sort of what's nice about this new formula here, is we don't have to worry about that. Okay, so let's go and find, go ahead, we're going to start with r of t equals a cosine t I plus a sine t j. We're going to go ahead and we're going to find the curvature of a circle of radius a. Now, before we start, actually, I'd like you to think about this question. Do you think the curvature would vary depending on where I was on the circle's circumference? Yes. Let's calculate this. All right, so r prime of t, we know we're going to need that. Remember, we're trying to build this formula. K equals the norm of t prime of t over r prime of t. So we're trying to build that formula. So keep that question in mind too. Do we expect this answer to vary or be constant? Okay, so let's find these things. Well, the derivative of this is going to be negative a sine t, comma a cosine t. Okay, and we might as well go and get the denominator of this thing right away. We need the norm of r prime of t. Okay, so the norm of this thing would be, well, it's going to be everything squared, added together, and then the square root. So it's going to end up being negative a sine t quantity squared plus a cosine t quantity squared square root. That turns out to be a squared times sine squared t plus cosine squared t square root. But that's just a. Alrighty then. So we end up with k equals the norm of the unit tangent vector derivative over a. Next, we need to get t prime of t. So before we can do that, we got to get t of t. Well, a unit tangent vector is the tangent vector to the function over the norm of the tangent of that tangent vector. That's what we would have. Okay? We actually have both of those things, don't we? Right? This was equal to negative a sine t I plus a cosine t j over the norm of that, which we knew was a. So we end up getting negative sine of t I plus cosine of t j. So there is t of t. Okay, that's not what we want. We want the norm of t prime of t. That's what we're trying to find. So we need to get the derivative of this thing and then take the norm of that result. So here we go. T prime of t would be derivative of negative sine negative cosine t I plus negative sine t j. And then if I take the norm of that, over here I just get negative cosine t squared plus negative sine t quantity squared square root. That's just 1. So we end up with the following fact. We can say that curvature is 1 over a. Now, I could also, just if I wanted to, I could write k of t equals 1 over a. Sometimes curvature will be a function of where we are. Okay? But notice that this expression doesn't care what t is. That's sort of what we suspected. right? That a circle would have constant curvature. Finish. The way to finish is to ask yourself, does this seem like a reasonable formula for determining the curvature of a circle?